One last thing before this segment of videos is done is I want to give you a quick recap about how summations work. So this is a concept that you've seen many times, probably in Calc 2, probably in discrete math, but it's critically important that you have a good reference for this going forward in algorithms. So this whole video is just going to be a refresher on summations. All right, so what am I talking about? I'm talking about this big sigma notation. So if I write something like this, so let's say I equals 0 to n minus 1, and then I put something on the inside of this, so say I put a number a. What does this mean? Well, this literally means a, and then a bunch more a's, plus a, all added together, right? So how do I know how many a's? Well, I use the limits on the sigma, right? I use the limits on I. So this is I equals 0. That a corresponds to I equals 0. Then this a corresponds to I equals 1. And then we've got a 2 all the way up to n minus 1. Right? So I use this as an index for the sum. And so you can think of this literally as a for loop, where at each iteration of the for loop, we're adding another copy of whatever's on the inside of the sum. Right, so literally this is just n times a. Okay, we'll often have some limits that don't just start at 0 and go to n minus 1, and so this generalizes quite nicely. Right, I can say this is, I could also write this as I equals k to L. Right, so I start I equaling k and I run it up and I include I equals L as the last one. So now this is, again, let's just sum this constant a together. So this is equal to a plus all the way up to plus a. And so exactly how many terms do we have here? Well, I starts out at k, and then we have k plus 1, and then we continue up. I'm going to write so plus a. We continue up all the way to L minus 1, and then L. So how many are there altogether in here? Well, we ended at L and we started at k, so there's going to be an L minus k term. And then to account for the fact that our sum is including both I equals k and I equals L, we have to add another one. I won't prove that to you here. Do it yourself. It's super easy. Just convince yourself that that plus 1 is necessary, right? That it's not just L minus k. Okay, so suppose I have something like this. I can treat this like any other sum. So I can do all kinds of factoring. I can split apart the sum into two different indices. I can do whatever I want. Right? So what's a fact about sums? Well, suppose I had this. So suppose I had a times b plus a times b plus a times b all the way up to plus a times b. I could factor out either of those numbers. Right? If a and b are numbers, I can just take a and pull it out of the sum. So this is exactly equal to a times b plus 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 b, right? No problem. And so what's another way to write this? I can write it like this. I can write I equals 0 to n minus 1, or whatever, of a times b equals a times I equals 0 to n minus 1 b equals a times b times the sum from I equals 0 to n minus 1 of just 1, right? And this thing here evaluates to n, so the whole thing in the end is just a times b multiplied or added together n times. Okay, so there's all kinds of things I can do with factoring and with splitting these things apart. Now, real quick, why do we care about sums? It's because these sums capture the runtimes of loops, right, of for loops. So if I have a loop like this, where I go for I starting at 0 and running up to n minus 1, and then I've got an inner loop that goes like this for, say, j starting at I to n minus 1, and then I have some operation. I might ask, how long does this thing take to run? Right? How many times does this operation get executed? Right? So how many times executed? Right? There's some shorthand for you. Well, I can just express this in terms of a sum. Okay, so this, I can just take the limits of the for loops and drop them directly into sum limits, and I'll have my answer. And then I can use the rules I know about manipulating sums to get it. So what do I have? Well, this is the sum from I equals 0 to n minus 1. Right? So each time this sum ticks, it's like the outer for loop in this nested for loop ticking. Okay, and then what's on the inside of this? Another sum from j equals I to n minus 1. And then what happens on the inside of the inner for loop? I have one operation execution, right? I just execute that operation one time. Okay, so this is now an expression that exactly captures how many times that operation is executed in that doubly nested for loop. Well, let's evaluate this. Okay, we might as well actually use the rules we have so far to try to get an expression for this. Okay, so let's look at this. So what do we have? We have always with these, always start on the inside first. So factor out whatever you can and then start on the inside and work from there. So I'm going to leave the outer sum alone and then work from the inside. Now, from the standpoint of the inner sum, I is just a number, right? So I'll just treat it like a number. I'm not going to treat it like anything special. I'm not going to say I is I. I've got to remember that I is some index from some other summation. No, I'm just going to treat it like a number, right? It's a variable that has a number stored in it. So what is this? Well, if I just evaluated this sum by itself, what I'd get is n minus 1 minus I plus 1. Right? That's it. Right? I'm just adding a bunch of ones together, starting at I, stopping at n minus 1, right? And I'm including both I and n minus 1, so I have to add that extra 1. So what is this? This is just n minus I. Okay? It's just a mathematical expression, right? So that inner sum evaluates to this mathematical expression, so then I can plug that in right here, n minus I. Okay. So now there's a couple things we could do with this, right? We could split this apart into two different sums if we want to, or we could try to just manipulate it in here. I recommend that until you're very comfortable with these things, you painstakingly split everything apart. So let me do this. Let me say this is equal to, whoops, there we go. So this is equal to this sum split apart. So now what I've got is I equals 0 to n minus 1 of n. So there's one sum minus I equals 0 to n minus 1 of I. Okay. So what have I just done? Well, I basically just said the following. I just used the fact that if I had a sum that went like this, a plus b plus a plus b plus dot 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 plus a plus b, right? A sum that is two terms added together at every single tick. I can just separate out those two terms, right? This is the same thing as writing a plus dot 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 plus a plus b plus b plus b dot 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 plus b. Okay, so that's all I did is I took this. I said there's a difference or a sum happening inside the sum end, so I'll split that apart into two separate sums. Okay, so let me actually move this over here so that it doesn't bug us, and I'll just continue. Okay, so now I've got these two sums I need to evaluate. I know how to do this one already, so let me do that one first. So this one I can factor out the n. So why can I factor out the n? Because it is not a function, like it doesn't change at each iteration of the loop. So this guy equals exactly n times I equals 0 to n minus 1 of 1. Okay, so there's 1. And now I don't know how to deal with this one yet. So this one is I equals 0 to n minus 1 of I. So I'm going to leave it for a moment. So I haven't shown you how to deal with this one yet. So let me save this one for a little bit later. I can finish evaluating the first one though. That's not a problem. So the first one just evaluates to n squared. Okay, why is it n squared? Well, look, there's a there's this piece here where there are exactly n copies of 1 added together. So this piece just equals n, and it's times n on the outside. So this is n squared. And then minus this mysterious sum, I equals 0 to n minus 1 of I. All right, so how do I evaluate this I equals 0 to n minus 1 of I? Well, let's think a little bit about what this is doing. What this is doing is it's saying, all right, so let me keep track of my index. So I equals 0, I equals 1, I equals 2, all the way up to n minus 1. When I equals 0, I add I into the accumulated sum. So what do? I add in 0. Then when I equals 1, I add in 1. So I have plus 1. When I equals 2, I add in 2. Why am I adding in 2? I'm adding in 2 because I'm adding in I every single time here. So I have plus 2, plus all the way up to plus n minus 1. Right? This is a triangle. So what do I have? You know, if I were to write this out in unary, right, in just where I have one symbol and I get to write down the number of symbols to represent the number, this looks like nothing plus a dot plus 2 dots plus 3 dots plus 4 dots, you know, all the way up to n minus 1 dots. And here there's n minus 1. Okay, and I know how to deal with that. In this particular case, because I'm going from 0 to n minus 1, it happens that this exactly equals, you know, I'll leave the n squared just drops down from above. So, and then this is minus 1/2 n times n minus 1. Okay. And then if I were to evaluate this out completely, what do I have? I've got n squared minus 1/2 n squared plus 1/2 n. And so in the end, I have 1/2 n. Whoa, dear. Oh, dear. There we go. I think I'm back. Back. Okay, good. 1/2 n squared plus n. All right, that's my final expression. Okay, is this guy here. Okay, so there was a bit of a bunny trail from where I began, but in the end, what did I show? I showed that this thing here, this doubly nested for loop, has exactly this many operations, or this many executions of its innermost operation. And notice that this is exactly, you know, I can factor out an n, and I get 1/2 n times n plus 1. Right? And so this is an expression that I showed directly from that for loop, informally in the synchronous session the other day. But here's another way to derive it using summations. Okay. So now let's think about this piece and carry it forward. Right. So I wanna just mention that you can think of this as a formula. So you can think of this particular expression as being a formula. So the summation from I equals 0 to n of I literally evaluates to this. So it evaluates to 1/2 n times n plus 1. Okay. And so what if I give you something like this? So consider this expression, I equals 0 to n squared, right, of I. Right? So if I count all the way up to n squared, what do I get? Well, I just think of this as a formula. And whatever I find here, I plug into those points right there. So I just end up with 1/2 n squared times n squared plus 1. Done. Right? That's as simple as that. Okay? All right, so suppose I gave you something like this. So I'm going to give you a similar expression to something I did before, but it's not going to be identically the same. So what if I gave you something like this? So I equals 0 to n, and then j equals 1 to m. right? So two different sum limits here. And then on the inside, I have I. So what I can do with this is I can say, hey, look, that I is only a function of the outer sum's index. It's not a function of the inner sum's index. So I can factor that I directly out of the inner sum. Okay, so I can say this is exactly equal to I equals 0 to n of I times j equals 1 to m of 1. So now this j equals 1 to m of 1, that I can just evaluate using my rules that I showed earlier. So this is, I'll leave the outer sum alone, I'll leave the I alone, but then I can actually evaluate this inner sum. So I can say this inner sum is m minus 1 plus 1, right? This is just the KL formula I showed earlier. And those ones, of course, cancel, so this is just m. So now this equals I equals 0 to n of I m. And now m is a constant in the sum limits that we see here. So I can just factor out m. So this is m times I equals 0 to n of I. And I know a formula for this piece, so I can just plug that in. So in the end, I get m divided by 2 times n plus 1. Right, and there's my answer. So something to notice here is that as soon as I was here, I could have factored out that second sum from the first one. So let's chase this in an alternate universe. So let's go into an alternate derivation down here. And I can say this is exactly equal to the sum from j equals 1 to m of 1. Treated now as a number, right, as an expression that was factored out of this sum, I equals 0 to n of I. Right, so by noticing that this piece here does not depend on I know that this piece here is a number, right? It's just something that I can factor out, something that's being copied identically every single time the I counter ticks. So I can just factor it out, no problem at all. And then I end up with this expression, which if I wanted to, I could chase down and it would take me directly here, right? As soon as I evaluate that j sum. Okay, so this is going to take plenty of practice and thinking about it, and you'll need to have lots of time to build up your confidence in these things. But if you're careful about which pieces depend on which indices, you can do some really interesting kind of fancy factorizations with these. Okay, so let me do a geometric series, just so as not to make this video stretch on for too long. Let me do a geometric series, and then I'll do a harmonic series, and then I'll be done. All right, so let's think about a series that goes like this, where I have A plus AR plus AR squared plus ... plus AR all the way up to the power of n minus 1. Okay, so what is this? Well, this is exactly equal to the sum from I equals 0 to n minus 1 of A times R to the power of I, right? So this one here, is I equals 0, right? What's R to the power of 0? It's just 1, so I just have the A. This one here is I equals 1, so what's R to the power of 1? It's just R, and so on, right? So on. Okay, so this is something that'll show up quite frequently in your first homework as you're thinking about solving recurrence relations, and it's useful to know that there's a nice kind of compact expression for one of these. All right, so I can rewrite this. Let me make the claim. I can rewrite this in the following way. I can say this is equal to the sum from I equals 1 to n. Right? So I have exactly the same number of terms, and I've just shifted my indices a little bit of now AR to the I minus 1. Okay, why is it the same? I can just match terms and see that it's the same. So here in the first one, I have R to the power of 0 is my first term, and then the power just indexes up. Here, again, I have r to the power of 0 as my first term, and the power just indexes up. Okay, so I have these two. These two are equivalent expressions. They mean exactly the same thing. And I can write either one of them as the following. I can say this is equal to a times 1 minus r to the n divided by 1 minus r. Okay, so this is a very powerful expression. Right? This is an extremely useful thing that you will find helpful on the first homework. And notice that there's also two ways of writing this, and I find it intriguing that it doesn't feel like this is true, but I can also rewrite this in exactly the same to mean exactly the same thing like this. I can say this is equal to r to the n minus 1 divided by r minus 1. Why are those equivalent? Well, because in this one I've factored out a minus 1. This one I've factored out a minus 1, which swaps the sign between the 1 and the r term, and then the minus 1s cancel each other. Okay, and so there's a special case here, right? So this expression is true for any a for any r. So this is true for all a and r. But if I have a special property that's satisfied, if I have this special property, if the absolute value of r is strictly less than 1, then I get an even simpler expression. I get something like this. I get this fact that I can actually add on infinitely many of these, and this thing converges to a nice limit. So if I have r, the absolute value of r strictly less than 1, then what I get is the following. The sum from I equals 0 to infinity, right? The sum with infinitely many terms in it, of a times r to the I just simply equals a divided by 1 minus r. Okay, and you can work that out just by taking the limit as, first assume that the absolute value of r is less than 1, and then take the limit here as n approaches infinity, right? And you'll end up with exactly this expression. Okay, so that'll be a handy thing going forward. One last thing I want to talk about is something that looks very similar, but it ends up being quite different, and that's called a harmonic series. Okay, so a harmonic series looks like this. Okay, a harmonic series is 1 plus 1/2 plus 1/3 plus, and then so on, right? So it's just 1 divided by the kth natural number, right? So let's say Hn is defined as the sum of the first n terms in the harmonic series. So Hn is called the nth harmonic number, and it looks like this. It's the sum from I equals 1 to n of 1 over I. And it turns out that this doesn't lend itself to a nice formula. It's not like the geometric series where we get this really nice cancellation and stuff that works out nicely. So I'll just say no nice formula. However, it turns out that Hn is big theta of log n. Right? So Hn doesn't have a nice formula to it, but if you were to plot this, it would be shaped just like the log function, right? Which is a strange and deep consequence of some cool stuff in math. Not at all obvious up front, but it turns out to be true.